Ma'am, we are live on YouTube.
Have you started local recording as well?
I'm starting, ma'am.
Yeah.
Yes, ma'am. Local recording has started.
Okay. So I think we can start now. By the time we are through with introduction, all the participants will join by then. So let me start. So participants, I extend a very warm welcome to all of you. I would like to welcome all of you and our first speaker of the day, Dr. Shumaloy Roy, to this 11-week Learning Physics with Conceptual and Problem-Based Approach program organized by NASI Delhi chapter. So, Dr. Shumaloy Roy, it is a very, very pleasant duty for me to introduce you to the participants. Dr. Shumaloy Roy has been working as an assistant professor UGC in Department of Physics and Astrophysics, University of Delhi since 2016. He completed his PhD in physics in 2012 from Indian Association for the Cultivation of Science, Kolkata, Jadavpur University. He has served as postdoctoral researcher in Max Planck Institute of Microstructure Physics, Germany from 2012 to 2015. His research interests include experimental condensed matter physics, physics of surfaces and interfaces, and nanoscience. He is the reviewer of Nature Publishing Group elsewhere. He is also the member of German Physical Society and American Physical Society. He has been principal investigator for UGC funded project, UGC Startup Grant for Faculties joined under Faculty Recharge Program. So, Dr. Roy, you are most welcome to join us on this program, and I request you to kindly start your presentation.
Okay, thank you, Dr. Bilal, for your kind reintroduction. So, okay. So now is it visible, my screen?
Yeah, it is visible. Could you please make it full screen?
I'll make it a slideshow.
Yeah, it is absolutely fine now.
Okay, thank you. Okay, so let us start today's discussion. Actually, we were discussing from last 3 days, 2 or 3 lectures. I discussed the crystal structures, 2-dimensional, 3-dimensional lattices. And last day I also said that today we will start something reciprocal lattice and diffraction. And let me see how far can I do, because this is a huge, I would say, huge topic of discussions. So it is not actually possible to complete every aspect within a day. Well, let me see how can we proceed. But before that, let me tell you that this will be up till now the crystal structure 1 what we have discussed. That was that was something was related to the BSc syllabus taught in the Indian universities, and some was overlapped with the MSc syllabus taught in the almost all Indian universities. But here today what we will discuss is more towards the MSc physics. I mean, less towards the BSc physics. So with this introduction, let us start this reciprocal lattice and diffraction. What do we mean by them and what are those? First of all, so when I start with anything we start with question comes to our mind that why should we study this? So the first question comes, okay, why should I study reciprocal lattice or reciprocal space for that matter of fact? I mean, why do we need the concept of reciprocal lattice or reciprocal space? Now you see, how do you study a crystal experimentally? We do normally, what we know from our knowledge in BSc is that we normally do a diffraction experiment, and conventionally we can do it with an X-ray, because for diffraction to occur, your aperture of the diffracting object or your sample has to be of the order of the wavelength of the electromagnetic wave. Now, the lattice constant and also the interatomic species in any solids are of the order of few angstroms, as you know. We have seen that In case of sodium, it is about 5 point something 6 angstroms or something. We have seen that sodium chloride, 5.6 angstrom Lattice source. So that means that, and the nearest neighborhood spacing is about 2.82 angstrom. So these are of the order of angstroms. So we need to have an electromagnetic wave for diffraction to occur, which has a wavelength of this much, about 1 angstrom or so. Now, X-ray was found that X-ray has a conventionally, I mean, the X-ray we are using, it has the wavelength of that order, like one from 0.1 angstrom to 10 angstrom, or something like 100 angstrom. So that's why X-ray has been a very useful technique to study the diffraction experiment in a solid state or in solids, whatever it is. But one must remember that X-ray is not only the probe with which we can study the diffraction in a solids. We can study the diffraction in a solids with electrons. We can study the diffraction in a solids with neutrons. So X-ray is not only the probe. But conventionally, for a bulk material, X-ray has been used over the 100, I mean, almost more than 100 years now. So this is a kind of conventional experiment, diffraction experiment, to study the lattice structures or the lattice spacing in a solid. Now, how do you do it? This is the picture on the top actually gives you some idea about the schematic diagram of the experiment. You shoot an X-ray to the sample, and then it diffracts, and the diffracted beam, which is this arrow, diffracted beams fall on the diffracted beams fall on a screen. And if you see then that and the scattered beam, scattered X-ray beam falls on the screen. The scattered beam is but the scattered from the direction of the incident X-ray. So this angle is theta. The scattering angle is theta. So it is scattered at an angle theta. Now, if I look at the screen where the X-ray falls, we will see that some of the spots like this, which is low in the lower half panel of the slide. So we will see some spots like this. So X-ray has incident on these spots, and we can see that this is the X-ray diffractive ground from the sample. Now, this is one way of seeing it. Another way of seeing it, if we have a detector which can detect the intensities of these spots, right? So which can detect the intensity of the scattered X-rays, then we can plot this intensity with the angle theta. That means at which angle, what scattering angle, what intensity of X-ray we have. So on the left-hand side, I have shown you a typical lab data. What we normally do with the lab is the following thing. So we plot them, intensity is a function of theta. And we can see that we at different theta we have some peaks, and at other theta we don't have any intensities, which is zero completely. So that's why that is same what we see on the diffractogram. You see the spots are the higher intensities, and in between that there is nothing. So this is exactly only thing is that we are recording the intensity of the each spot. On the left hand side, that is this plotting. So this is called a typical XRD spectrum or X-ray diffraction results from something that the red and black peaks or the curves, you don't have to differentiate. These are from two different samples. This is exactly from my lab. So that's what I just put it as an example. You don't have to know much about this. Only thing is that a typical X-ray diffraction result looks like this. Just a moment, I open the chat window so that anybody who has a question in mind can interpret. So that is one. Okay, next, this is a typical diffraction experiment. We all know all of us know about it. Now the famous mathematical laws, which governs this diffraction, is basically this Bragg's law. All of us know 2d sine theta equal to m lambda, where theta is the angle scattered, and d is the interplanar spacing, and m lambda by 2. This is 2d sine theta equal to m lambda. M is the integers, and lambda is the wavelength of the X-rays falling on the sun. Now, if you see this equation, carefully, so sine theta equals to m lambda by 2 into 1 by 2. And what we determine from the experiment is the theta or sine theta, whatever you say. We cannot determine d directly. What we determine is sine theta. And sine theta is actually proportional to 1 by d if lambda is constant, as you can see. And what is 1 by d? D is the distance in the real space. Now 1 by d has a dimension of length inverse. That means the diffraction experiment, what we are doing, is giving directly a space or results which is a length inverse. It never gives you d, it always gives you a sine theta or theta. You can always find out d from it in the real space, but what the experiments directly gives you is 1 by d. It's not. So it is implied in the experiment, it's in the equation that the diffraction, all diffraction experiment, what we do it in the reciprocal space, right? It is 1 by d what matters. And it's 1 by d is direct information of the reciprocal space. So diffraction experiment will give you direct information. Okay, so that is the reason that we study the reciprocal space so intensively. To know the features of a crystal, to know the features of a lattice, we do a diffraction experiment, and the diffraction is exactly what you see in diffraction is exactly the reciprocal space, not the real space. Okay, so if that is done, let us go to the next slide. Uh, okay, as we have studied the uh, now we have studied this one, Bragg's law. We can solve this problem now. 2D sine using just 2D scientific dynamics. So a narrow beam of X-rays with wavelength 1.5 angstrom is reflected from an ionic crystal with an FCC lattice structure with a density of 3.32 gram per centimeter. The molecular weight is 108, and you have to find out the lattice constant. So I would request all the students to have take a pen and paper and just try to calculate it. As we can do it along the way. I will just show you the solution. It doesn't happen. So at least you start with the problem and tell me how you will proceed. So anybody in the audience or in the students, just tell me in the chat box how you will proceed for the part A. Say. Forget about the calculations. How will you proceed? So you have to find out the lattice constant. Can we proceed somewhere? Using density formula. Arya Gauri said using density formula. By density formula, what do you mean? Can you density, I know the density of a substance is mass by volume. You mean that? This is your rho is equal to Zm. Smriti Bhai Chakraborty said rho equal to Z into M by N A cube. Now see, from the day one, the problem I have been solving and I am telling time and again, don't put so much emphasis on your memory. Okay, don't put emphasis on your memory. Don't mug up these formulas. This formula or these things is always going to be deceptive because in the exam time you may not remember this formula. So I would rather suggest that go by definition and solve it. Arya Gori said this is density, not rho. I don't know, whatever it is. Rho is also sometimes it is density. But the point is, whenever you try to remember the formulae, there is always a chance to forget this in the exam hall. So from the beginning, you will see, must have seen that I have not put stress on much, would not stress on much on this remembering the formula. Bragg's law will come later. This part A doesn't have anything with the Bragg's law. The second part will have the Bragg's law. So Sri Lakshmi say wavelength, Bragg's law. So these will always come in the second part. not in the first part, because in the second part it is the sine of the angle corresponding to 1, 1. I am saying the first part. Okay, now let us start with this problem. Now, last day, okay, yeah, fine. So last day, let us start it. Z is equal to 4, mass is given, very good. Arya Gori said. So last day we did the number of molecule in a FCC lattice like sodium chloride. We did it, right? We did the problem, we solved the problem. Number of molecules in a unit cell was 4. Last day we did it. Okay, so that we can do and solve the problem like this. So number of sodium chloride molecule 6 angstrom, I know Srilaxmi, but I just want the problem to be done not from the formula but from your understanding. Okay, number of sodium chloride molecule per unit cell is 4, that we have seen last day. Now if I express A in centimeter, then the what is density is 3.32 gram per centimeter cube. What does it mean? That 1 centimeter cube contains 3.32 gram of the substance. That means if I express my A or the lattice constant in centimeter, that means A cube centimeter cube of sodium chloride contains 3.32 A cube gram. Isn't it or not? If 1 centimeter cube contains 3.32 gram, A cube contains 3.32 A cube. Now 4 molecules contains in A cube that we have seen, and then 4 molecules of sodium chloride weigh 3.32 A cube gram. And according to the problem, 1 gram mole of NaCl is, it is not NaCl, but I have written those, forget it. I mean, the name is not important. So 1 gram mole of the FCC lattice is 108 gram, which contains 6.023 10 to the power 23 molecules. So all we have to find out what is the weight of 6.023 on 10 to the power 23 molecules. We know the molecules weight of 4 molecules. We have to find out the weight of 6.023 to the power 23. So if I know the weight of 4 molecules, we can know the weight of 1 molecule. We can find the weight of 6.023, and that is the left hand side, and that is equal to 100. Now see, in this problem, the way I have solved, I don't have to remember any formula. Only thing that I have to know understand the definition of density, and of course these other things. That's all. And if you solve this, you get the A has, it becomes something as 6 angstrom. So that's what I wanted to point. I wanted to stress time and again. Please don't depend more on your memory, but depend more on your understanding. Okay, I didn't use any formula in this problem. Now, if we have done the part A, part B is very easy. This is a FCC structure. Acha, Sweta has asked a question, sir, why we plot 2 theta instead of theta in axis? Okay. Well, Sweta, I mean, that is nothing to do with, I mean, for our time again, but since you have asked, let me answer. So 2 theta is the scattering angle, and all of the softwares which you normally we use in X-ray diffraction diagram, they plot the 2 theta normally, because 2 theta is the scattering angle. Theta is the angle between the incident X-ray and the surface, and 2 theta is the angle, is the total scattering angle 2 theta. So it doesn't matter, you can plot also theta. From 2 theta you can find theta. You can many ways, many places you will find theta also, but many a place by the convention, by the definition, they just plot 2 theta, because 2 theta is a scattering angle, whole scattering angle. Okay, and the detector rotates in the angle in the circle which is called 2 theta circle. But that is merely a convention. You don't have to stress too much on it. Okay, that is the answer. And the next part, the problem number, in the problem is B. So we have to find out the, of course, if we have to find out the sine of the angle, we have to find out the interplanar spacing D111 of the reflection, and that we can find out for FCC lattice structure. We know it is square root of 1 by square root of h bar square plus y k square by b square plus l square by c square. This formula we last day also we discussed. So we can find out the relation between D1 and A. If we know the relation between D and A, we can find D, and then we can use Bragg's law to find the sine of that. It is easy. Whatever, root 3 by 8. I'm not interested in the answer that you have to calculate. Leah. Leah. So I'm not interested in the answer. I'm interested in the way to solve. That is more interesting. The answer you can check yourself. Okay. So this is one problem. The giving one problem has a certain idea behind it. This problem was to give an idea that don't depend much on your memorizing capability, depend on your understanding capability. Okay. Now about the reciprocal lattice, I have started with some conception that why do you need reciprocal lattice? Then, but these are all these mathematical formulas done in any book, so we can follow any of the books and find out what is happening. I mean, all these formula. These are very common thing. The basis vector in the reciprocal space. It is V1, V2, V3 is comes as this cyclic formula of A1, A2, A3. So what is this? A1, A2, A3 are the basis vectors in the real lattice, and B1, B2, B3 are the basis vectors in the reciprocal lattice. So if we know the basis vectors of a real lattice, A1, A2, A3, we can find the basis vectors in a reciprocal lattice. And they are related, and they have certain property which is written in the last line of the slide, that Bi cross Aj is 2 pi into delta Aj, right? So that means that this Bi into Aj is only gives you 2 pi when I equal to j, and otherwise it's 0, right? So that means at least with the two vectors in the real lattice, that is a one reciprocal lattice must be perpendicular to them. So if A1, A2 are there, so B1 at least one vector has to be perpendicular. But these are the all properties you can study in your book. Any book will have all these things. And A1 dot A2 cross A3 is nothing but the volume. That's why I've written like this. B is the volume of the unit cell in the real lattice. Okay, so with this, after that, this is also very common. All of you must have studied this, that if I, with these basis vectors, we know what are the basis vectors of a simple cubic lattice, what a body-centered cubic lattice, what a space-centered cubic lattice. If we just try to convert them into the reciprocal space, simple cubic remains simple cubic, body-centered cubic remains becomes face-centered cubic, and face-centered cubic becomes body-centered cubic. So every standard textbook actually discusses this. And the only thing is that the lattice constant, which is in the real space for all these cubic lattice, if it is A, the lattice constant becomes 2 pi by A. This is just one table for just to look at, I mean, just to give you an idea what happens in a reciprocal space if I transform the cubic crystal to into the reciprocal space. Okay. Now this thing we studied last day, a face-centered cubic material transformed. This problem we did on the last day. From this so this is an example. How can I transform the FCC? So there is a question from Aman. Sir, what is the purpose, importance of reciprocal? So you were there from the first initial of the lecture. I have discussed all these things. What is the importance of reciprocal lattice? Why do you study? My first slide was why do you study reciprocal lattice? Perhaps you missed those. So see, my first lecture, the first question which I start is, why do we need the concept of reciprocal lattice to know the question? Perhaps you were late, but the point is very simple, that all diffraction experiment, if you see the Bragg's law, you determine in the diffraction experiment, you determine theta, that is the sine theta. And sine theta is proportional to 1 by d if your wavelength is constant. So 1 by d is something which is a length inverse property, 1 by d. So that is inverse space. 1 by d is a reciprocal space information. So the diffraction experiment will directly give you theta, not d. So from, of course, from the sine theta, you can, from 1 by d, you can convert it to d. But what you get directly from any diffraction experiment is 1 by d. And to know the lattice structure, we always do the diffraction experiment. And that's why we come to know the reciprocal space. Okay. That is the importance of reciprocal space. So far so good. What we are discussing that now, the last year we did this problem, we solved these problems, and we came to know that these are the basis vectors of an FCC lattice, A1, A2, A3. So if I have this A1, A2, A3, I can find out what is B1, B2, B3 from the formula. That is no big deal. So one can find out. Similarly, if you have a BCC lattice in a real space, you can find the what is the reciprocal space lattice, and you will find that these are only the FCC becomes BCC in reciprocal space, and BCC becomes FCC in the reciprocal space. So all these things you can do as an exercise. I mean, it's discussed in all the books also. But since we are discussing, let us do this problem. A lattice has the following primitive vectors: A2 plus J plus K, B2 plus K plus I, and C2 plus I plus J. Now, just before this slide, I kept this slide as an FCC lattice. You see FCC lattice, this is A1, A2, X5 plus. So whenever you see such a set of vectors, which is like a cyclic thing like this, we can readily identify that these vectors are nothing but the primitive vectors of an FCC lattice. Now, when you can identify that these vectors are the primitive, you don't have to solve the problem. You can directly say which one was. So we know that if it is an FCC lattice, it will be a BCC lattice. Now, if we know the what will be the if the lattice constant is A, then in the reciprocal lattice it will be 2 pi by A. Now here from the definition of the lattice, what is the lattice constant? Can you tell me what is the lattice constant? Can you identify from A is equal to 2J plus K, B is equal to? It's very easy. Pi. Not I am asking what is the lattice constant of the FCC lattice in the real space. Yes. So very easy. What is somebody says 2, somebody says 4. Let me see. So what was the for A1 is A by 2 x plus 1. Here A is equal to 2 into J plus A. So what is the lattice constant? So A1 here has to be A by 2 into x plus y. A is the lattice constant. Now here it is given like 2 into J plus K. What is the lattice constant? Simple. Yes, now everybody says, but Sri Lakshmi said it correctly for the first time. It is 4 angstrom. Yes. Arya said 4. Good. Now everybody understood it. It's a 4 angstrom. Now if it is a 4 angstrom, then what will be the lattice constant in the BCC lattice in the reciprocal space? It will be 2 pi by A. Pi. There is no answer as pi. Yes. The answer is pi by 2. So it is 2 pi by 4. That is pi by 2. Okay. So the first answer is correct. BCC lattice with cubage of pi by 2. Yes. Pi by 2. Thank you. Everybody could do it now. Very good. So you see, these are the very simple problems, and this kind of problem actually appears in your all the exams, public exams, GATE, NET, and all these things. All you have to have is the idea. If you suppose if you don't have the idea of this, that this is an FCC lattice given, A is equal to 2J plus K is an FCC lattice, then you have to apply those formula. B1 is equal to A1 A2 plus A3 divided by A1 dot A2. You have to calculate everything. But if you can identify that this is a FCC lattice given, then at once without doing anything, you can write down the answer. So the having idea is very important. Okay, so with that, There is another problem with the reciprocal lattice. So when there is a three primitive vectors, it is easy to do a1 and a2. But in two dimension, there is no third vector. So what will you do? So this is one example of such that the real space primitive vectors for a two-dimensional lattice. It is a two-dimensional lattice given by a1 by a2, a1 ax, a2 and a by 2 into x plus 3 root 3. Now the reciprocal space. What will be the reciprocal space? Now, in order to find out the reciprocal space vectors, unit vectors, what we have to do, we know the formula a1 dot a2 cross a3, but there is no a3 over here. So what one does over here, we take a3 as a perpendicular vector a into z along the direction, along the perpendicular to the plane containing, and then carry out the problem. So then there will be no problem. You can find out b1, b2, b3, but b3 will be simply this 2 pi by a into a3, but that doesn't matter. We have to find out b1. So this is the prescription for doing it in two dimensions. You can take only one vector along the z-axis and do the rest of it. Okay, so that is one. You can consider, I mean, there is no problem. You can consider a unit vector in the x-axis, z-axis also. But the point is, I mean, the volume has to become the AQ, right? So that you have to consider. You can do it. It's no problem. So this fraction, this A, you see, I can take any value. I can take 1 also, right? A3 is equal to 1 into 0. Because that will cancel out. Because there will be whatever calculation you do, there will be numerator. On numerator you will have an a3, in the denominator you will have an a3. So that will cancel. Doesn't matter. Okay. So now these are the another things of reciprocal lattice. For all of you know all these things, that we can now with this b1, b2, and b3 vector, we can also form a three-dimensional lattice. And if we can form a three-dimensional lattice, we call it a reciprocal lattice. Yeah, we can call it a reciprocal lattice now. And if we form a reciprocal lattice, it will be another Bravais lattice. So if we can identify or if we can define an origin like O, so any vector from this origin to any points on this space will have the value HKL, because we know that these points are nothing but the Miller indices of the planes from where we have in the real space crystal, HKL. So all these points in this space, reciprocal space, are nothing but the HKL planes. So these points are representative of the planes in the real space. For a set of planes, we have a single point. Like here is one point is HKL. And if the radius vector, or not radius vector, or if a position vector of a lattice point is G, it can be represented like this: HB1 plus KB2 plus LB3, because B1, B2, B3 are the basis vector. Sangeeta asked a question: why there is always 2 pi in reciprocal forms? This is a very good question. Thank you very much. So see, this 2 pi, if you, I don't know, this 2 pi, I need to have some equation to write. But if you see, there are some, what to say, in any lattice, any property has to be periodic, right? So suppose I have some a physical property at a point R, in R, it has to have a translational symmetry. That means n, which is a function of R, has to be equal to n, which is a function of R plus t, where t is the translational unit, the translational vector in a lattice space. This translational vector I discussed in my first class, that every crystal structure has this translational symmetry. Now, in order to have this equation, nr is equal to nr plus t, this actually comes nrt. If you take a Fourier transform of this, there is an exponential factor comes up, exponential I times some integer. And whenever this integer comes, unless it is 2 pi, it will not show 1. And then other than that, you will never find this as a unity. And this equality is not there. So in order to say, but these are the all mathematical equations, but in order to physically to answer this question is to maintain the periodicity of any properties like electronic density, magnetic density, you have to have this 2 pi. Now, the point is, without this 2 pi, we can do many calculations. I mean, conceptually, it won't be any problem. But when you do an experiment and measure the real things, real lattice constant, then there will be a problem. So it is always advisable to include this 2 pi. Okay. Garima Sri, what is the use of G to understand about the crystal? So first of all, G is the vector in the reciprocal stress lattice. So when you have a reciprocal stress lattice, of course you have to have a vector, like we have had a position vector in a real lattice. It is exactly like a position vector in the reciprocal lattice. Okay. Now, how does it? What is the importance of reciprocal lattice such like this O to HKL planes? It will be clear as we go ahead. But for the definition of the reciprocal lattice vector, it is nothing but the position vector of any point in a reciprocal space. That's it. That is the definition. And that is given by HB1 plus KB2 plus LB2. And as we know, G is actually, basically G is nothing but it is a perpendicular to the plane which is defined by this point, HKA. That you must have known from your textbook, all textbook discuss. You can prove this also. Okay, if I have done this with this is the property of reciprocal lattice, and we have to go to proceed from this. And let us again come back to our X-ray diffraction problem, Bragg's law. X-ray diffraction, Bragg's law, where we see there is an incident X-ray and the reflected X-ray. Okay. Now Bragg actually modeled the crystal as different lattice planes, which are acting like, parallel mirrors, which were reflecting the X-rays. So many times you will see that the Bragg's law of diffractions are said that Bragg's law of reflection. So Bragg reflected. It is not said Bragg refracted, it's said reflected. So this is a model for the lattice planes Bragg introduced. That these are the planes from which the X-rays are reflected, and this is a diffraction due to reflection. So the path difference produced in this between the two planes is due to reflection, and this path difference is the integral multiple of the wavelength, and that is the condition of maxima. So that is 2d sin theta by. So suppose this one set of such planes, parallel planes are like this. One set of parallel planes are like this, and X-rays are coming in and reflected. Okay. Suppose. Now, if it is so, let me introduce the wave vector form of this Bragg's law. Wave vector means the direction with the incident X-ray comes in, K, and K has a magnitude 2 pi by lambda. Veerapandian said yes, 2 pi gives the meaning of Fbian functional symmetry in the circuit. That's true. That's what I say. Any physical property, I mean, any function, unless you have this 2 pi, you don't have this symmetry. That's true, Veerapandian. That's true. Adumuga. Okay, that's true. Thank you. So now I replace this this incoming rays, as you can see, like as a vector K and K prime. The scattered vector is K prime, the reflected vector is K prime, and the incident vector is K. And what is the magnitude of this K? Can anybody tell me? K is a wave vector, so what is it related to? In an X-ray, in an electromagnetic wave. If lambda is the wavelength, what is the relation between K and lambda? That's it. That's it. That's true. Yes. Thank you. Thank you. So K is 2 pi by. Now my second question is, in this reflection, I have written the scattered vector is K prime. What will be the value of K prime? Is it different from K or it is the same? Same as K. Good. Swati answered correctly. Same as K, because we did not change the wavelength. Wavelength is not changed in this scattering. Lambda is same, And the direction has changed. That's why I put a k prime. But the magnitude is same. But the direction is different. But since it's a vector, so we put it as k prime. But you can always remember the magnitude remains same. So it is basically what is the physical reason that in this case, in the diffraction experiment, all the diffraction experiment you see, this k, the magnitude of k remains equal to the k prime. What is the reason? Anybody? Yeah, we'll come to the phase difference, but doesn't matter. Whatever the phase difference is. So that's why this angle is different. Huh? Arya said so phase difference will be there, right? Right. Of course. There will be a phase difference. But that is not my point. My point is why the magnitude is equal. Great. Fantastic. Swati answered in elastic scattering, and that is the correct answer. This is an elastic scattering. Any diffraction experiment is an elastic scattering where the wavelength doesn't change or energy doesn't change. Elastic scattering by definition is energy doesn't change. So the incident, if the lambda doesn't change, that means the X-ray energy doesn't change. So that's why any diffraction experiment we do is the elastic scattering. What we observe is that as a coming out X-ray is the elastically scattered X-rays. That's why it is at the same energy and same energy. So okay, so now we have the two vectors k and k prime, and you see I have designated these vectors at AO. O is some point where the X-ray is striking, and as I said, k prime will be same 2 pi by lambda. Now around the point O, I define the reciprocal lattice. Okay, so I have taken this because this is a plane, and this is actually a set of planes, and corresponding to the set of planes, there will be a point in the reciprocal lattice. So that point I have taken as my origin, and similarly, there's all other reciprocal lattice will be there. The reciprocal lattice point will be there. Okay. Now what I did, I drawn a sphere because k and k prime is the same by magnitude. Their length of the vector is the same. So with this length of the vector, I have drawn a circle, and this is called an Ewald sphere. And the diffraction only occurs for those points, those reciprocal lattice points, which falls on this sphere. This actually you know all of them. This is called Ewald's construction, and this is the condition of diffraction. So that means we always will have a reciprocal lattice vector if the diffraction is occurs, and if the point falls on this sphere, on the surface of this sphere. And the vector relation will be k prime. As you can see from this, you can apply the vector triangulus law of addition. This k prime is equal to g plus k. And that means k prime minus k is delta k, which is the difference in the scattering and the incident vector. And that has to be equal to g, and which is the condition of von Laue diffraction. Now, one thing is very serious. One thing is very clear from this discussion. You see, I started with Bragg diffraction, and I ended up with von Laue's diffraction. So this way, if you discuss the thing, that means that these two diffractions are not something completely different thing. They has to have a diffraction meaning of this diffraction. Since both of them are diffraction in the crystal, at some point they have to match, and this is a match. So they are not different at all. Bragg's diffraction and the von Laue diffractions are the same, but they have to be looked. They have to be looked in a different way. That is right. But the results will come all of the same because both of them are the same diffraction. Okay, so this is the von Laue's diffraction condition. Now, von Laue diffraction conditions, as we know, as we have discussed, k prime square is equal to k square because the magnitude of k prime is always equal to k. And if I apply this von Laus condition, this k prime will be k plus g dot k plus g and k square, this equation. And this equation will reduce us to 2k dot g plus g square equal to 0. And this equation sometimes called vector form of that. So actually diffraction to occur diffraction, you must have this condition satisfied in your crystal. Otherwise, with your X-ray wave vector k, you cannot have any diffraction. So for any diffraction to occur with your wave vector k, you must find in your reciprocal lattice vector a g, so that this condition is satisfied. And if this condition is satisfied, it is sometimes called Bragg reflected or sometimes called loud reflected. Both are the same. But this is the condition of diffraction. So whenever this condition is satisfied, we get a diffraction in whatever, in any substance. This is the condition of diffraction. So whenever this condition is satisfied, sometimes we call it Bragg reflected or sometimes we call it loud diffracted, but both are same. Okay, now let us go back to our previous definition of two-dimensional square lattice, what we discussed on the very first day. We have a square lattice here where A1 and A2 is equal to A, magnitude of A1 and A2, both of them, as the angle between them is nothing. It is very easy. Now, if we want to convert this into the reciprocal lattice, what will be the reciprocal lattice? Just tell me, anybody? What will be the reciprocal lattice and what will be the lattice constant of that in two dimensions? So you have a two-dimensional square lattice in real space. What will be the reciprocal space lattice? Great. So Arya said, so it will be now what kind of lattice it will be first of all, and then the lattice constant. If I convert it to reciprocal lattice, what will be the nature of that lattice? What kind of lattice it is? Simple cubic. This is two-dimensional. Anjali. Cubic. This is two-dimensional. Sangeeta. Where do you find cube in two dimension? Square itself. Correct. Sri Lakshmi is correct itself. It is a square. It's a square lattice. Exactly. So everybody said it's a square lattice. It will be a square lattice, but the lattice constant will be, what will be the lattice constant? Somebody said it previously. Yes, it will be square. Square lattice, Pawan said is correctly. And what will be the lattice constant of that square lattice? Is 2 pi by a. Fantastic. Many said this. Surendra Kumar said, no, not a. It is a reciprocal lattice. So it will be 2 pi by a. Okay, good. So everybody now know 2 pi by a. So this is the reciprocal of the two-dimensional square lattice. We have the axes as B1 and B2, and B1, B2 is 2 pi by a. The angle between them is pi by a. Now what I did, now let us do one thing. I replace the origin here somewhere in the middle. I take the origin in the somewhere in the middle. And if I take the origin in the middle, now you see these vectors, origin is on the lattice point, one of the reciprocal lattice point. So these vectors are nothing but the reciprocal lattice vector G, because this runs from one lattice point to other lattice point. These are nothing but G. This is one G which is perpendicular, this is one G which is horizontal. Now I draw a witness C cell on it, on this reciprocal lattice, around the center, around the origin. So what is the prescription for drawing the witness seal? This is that we connect all the points around it. So if I connect all the points around it, and then I mean the nearest point around it, and then intersect those lines, connecting lines, perpendicular bisector of those connecting lines, enclose a region in the space, that is called witness seal. Now here the four nearest point, if you join them, the weaknesses will be like this. The shaded region, these are the perpendicular bisectors, and the perpendicular bisectors encompasses this region, which is a square again. This is the weakness C cell. Well, if this is a weakness C cell, okay, so it's there. Now I draw all these 4 vectors around this lattice points. So these are all one of the G vectors. This the right hand point is 1 0. The left hand point is 0 minus minus 1 0. Something like this. So all these points I can coordinate with the coordinates and I can write the vectors. So these are all G vectors, reciprocal lattice vectors. Now in this reciprocal lattice vector, I draw my wave vector of X-ray which is falling on my sample K. Now first of all, my question is, can I draw this K in this reciprocal lattice space like this? I mean, what is the dimension of K?
Yeah.
1 by length, yes, 1 by length, that's true. So if it is 1 by length, I can always plot it in a reciprocal lattice, because reciprocal lattice we have the dimension of 1 by K. So I whatever vector which has a reciprocal which has a dimension of 1 by L, write it, I can draw it. So that's what I did. Suppose this K is one of such vectors. Okay. Now tell me, there is one G vector I have drawn. What is the component of this K vector on this G vector? Can anybody tell me? Now K dot G, the equation we have for the Bragg diffraction or Bragg reflection or Lau diffraction was 2 K dot G plus magnitude of G square is equal to 0. Now what is K dot G in this case? G I have shown in a diagram. So basically K dot G means component of K along the direction of G. What is that? What is the length of the component along the direction of G? Cos theta, that's I know. But you have to tell me the answer. The magnitude of the component along the axis G is very easy. Try to see the opposite direction of G. So G is along the downwards. There is only the upwards vector G. And if I take a component of this K on this G, it will be just half of G. The magnitude will be half of G and the direction is opposite. So the component of K on this vector G is minus half G. So K cos theta will be nothing but minus half G. Okay. It's very easy. You are taking a component along the vector, but the vector is in the downwards. You can take a component along the upwards vector G. And if you take the component, the magnitude of the component will be half of G. And since it is in the opposite direction, it will be minus half of G. So K dot G will be minus half G square. And if it is minus half G square, then 2 K dot G is minus G square. Minus G square plus G square is 0. That means for this vector, your diffraction condition is satisfied. Okay. So this condition is satisfied for this vector G, for this vector K. Now, if you are convinced with this, we can see more that representative vector. Any vector which starts from the origin and ends up on the line, on the top line of the Wigner C cell, Any vector which starts from the origin and ends at the top line of the weakness C cell like this, all of them will have this equation satisfied. Because for all of them, the component of along the g-axis will be half g square, minus half g square. I mean, minus half g. This will be half g square. So for all of them, this condition is satisfied. Now, similarly, as this structure has this symmetry of 90 degree, so similarly, we can say that all the vector which originate from the origin and ends up on the left-hand side of the boundary, they will also have a component of these chess vector g vector, which will be satisfying this equation. Similarly, a vector, all the vectors in the lower part, all the vectors in the right part. So the point is here, so all the vectors which originates from the origin and ends up the boundary of the weakness C cell, doesn't matter wherever it ends, will satisfy this condition, this back condition. Any vector which starts from the origin and ends up at the boundary. But if any vector starts up from the origin and doesn't end up at the boundary, it will not satisfy. The component then will be not half g. It will be less than that. So only those vectors which starts from the origin and ends up at the boundary of this weakness C cell will satisfy this low diffraction condition. In other words, all the vectors, all the wave vectors, or all the X-rays, wave vectors which starts from the origin and ends up at the boundary of this weakness C cell will be Bragg reflected or loud reflected. So the vector, all these vectors spans this area of the square. So you see then that is called the first Brillouin zone. So actually the first Brillouin zone is by definition is nothing but the weakness C cell. So first Brillouin zone is nothing but the weakness C cell. It is the definition of the first Brillouin zone is the locus of all the vectors which starts from the origin and ends up on the boundary of the cell. This locus is nothing but the region within the cell, and that is the weakness C cell. So when I defined the weakness C cell on the very first day, I told that this has a physical meaning. I will say in the along the course. So this is the physical meaning of this. This is just not a name. So it means that if I have a wave vector which starts from the origin and it ends up at the boundary of the weakness C cell, it will be Bragg reflected or loud. So there is a physical meaning of weakness C cell. Okay. Okay, almost my time is over. I have to discuss actually many more things which I didn't discuss, but I don't have time. It's a very important topic has been left, which is and this is actually due to this. I have shown you this this figure earlier from my lab. Is intensity versus 2 theta of this is an X-ray diffraction diagram, where you can see that okay, up till now what we have studied is the condition for diffraction, but none of them till now has been discussed. This Bragg diffraction condition, low diffraction condition. They did not talk about the intensity of the diffraction peak, because here you see an experimental diffraction from the diagram. At different angle we have different intensities, but this diffraction, Bragg diffractions laws and the low diffraction, they don't give any idea about the intensity, because these are nothing but the condition of diffraction, whether the condition of diffraction is satisfied or not. That is the Bragg diffraction or low diffraction. But to study the intensity, to calculate the intensity, what you need to know is the geometrical structure factor. So, but I think all of you have studied, or if you have not studied, you will be studying this geometrical structure factor. Actually, geometrical structure factor gives you an idea of the intensity, because intensity is proportional to Sg mod square. that is SG is nothing but the geometrical structure. It depends on the atomic form factor, and but I don't have much time to for all these things. What I can give you is the table for which you can see that there are for these different HKL values, the structure factor will be 0 for different structures. Like for simple cubic, any HKL is fine. For BCC, if H plus K plus L is even, then only you can see a peak. Otherwise, the structure factor is 0. And if the structure factor is 0, the intensity is 0. Similarly, for FCC, sodium chloride, all have different. Every year there are a number of problems comes into from this concept of geometrical structure factor. But this thing is very easy. It looks like this equation. When I look at this equation, it looks like very big equation, but these are very easy for simple structures like sodium chloride, VCC, FCC. For simple structure, this is very easy, and that's what comes in the exam. But I don't have time to discuss all this to you. And so let me thank you for your attention. And a special thanks to all my students.
Thank you, Dr. Shumulai, for such a scintillating talk. I'm sure the students have thoroughly enjoyed it. Thank you so much. Yeah. I think our next speaker, Dr. Senthil, has also joined. Dr. Senthil, are there?
Yeah, okay.
Yes, ma'am, he has joined.
Yeah. So I think it's time for us to start with our next talk. So Dr. Savita, could you please share the screen once again?
The recording first and then I will share the screen.
Yeah, I think you will have to stop recording and you'll just start again.